Okay. All right. Hello, everyone. I hope everyone is having a good day. My name is Umebewe Webedu. I also go by the name Great. That's the name most people know me as. Today our session is going to be building a process exporter, a macOS process exporter in Zig. Um, so just a little about me, not much. I'm currently a site reliability engineer at Botanics Labs. I'm interested in all things system performance, kernels, and networking. So let's look at our agenda for today. We'll talk about what a process exporter is, why was even this process exporter built in Zig. We'll talk about the concept of no proc file system on macOS or Darwin operating systems. We'll talk about how we got the data, like the necessary data to build this process exporter. We'll talk about like the problems we face, like the allocation trash, how we dog fooded with the exporter to detect the allocation trash. We'll talk about profiling with Tracy, talk about the memory strategy that was adopted. We'll look at the results of implementing those fixes, and then we'll look at the lessons learned. And if time permits, we'll go into like per process network starts or macOS. So, what's a process exporter? A process exporter is simply a daemon that discovers processes. It reads the starts from the OS, and optionally you could group them, by name, by user, like the user who owns this process, uh, the CMD line, etc., etc. So when you have an operating system, for example, you could a normal laptop, for example, could probably have up to 100 processes. So these processes have like something called a PID, which is like a process ID, basically a process ID. So what we are doing here is that we tell the OS, I want to get to the process IDs, and tell me about this process. I need more information about this process. So then, when we get all of that, we group them and then we expose them in some format meant for scraping. Right? In our case, we do that with the Prometheus text format. And something you should note here is that a process exporter is not a profiler. Um, is a cheap, repeatable snapshot for monitoring. So what that means is that we can, take a snapshot of the process stats at a point in time. So let's say right now at this moment, this is like you know, 3 o'clock, 3 p.m. So right now, this point in time, at this second in time, what is the start for this process? Then we take another snapshot, let's say in the next 15 seconds, then we could be able to plot a time series based on that data. So, so yeah, why this project exists? So I needed Prometheus style per process metrics on macOS for cost attribution on like a product I'm building. um, Sadly, there's no process exporter. There's no decent process exporter on macOS. Linux has this wonderful project called this Nabat or from process exporter, and it works really well. But you won't find anything comparable for macOS. And you might say activity monitor and top ad right there, but these are interactive tools. Like they don't have history. They don't give the ability to see historical usage, right? Like you can only see at a certain point, like right now. So yes, that is why I built this project. So yeah, let's talk about Zig. Why did I choose Zig for this project? First, like I said earlier, a lot of these, you know, um, a lot of these stats, a lot of these metrics, a lot of this data has to be gotten from the OS directly. Will come why we'll, in the future slides we'll see why that is the case. But it needed a lower level language, so I need manual control over allocations and how data is kept, like in lifetimes. I needed simple and very safe in say interrupt. And because there's no hidden runtime in Zig, it's easy to like keep the memory flat across scripts, like probably the same. And also Zig is a language I've been exploring for a while, so like it only made sense that, oh, I had a Zig itch, why not try it out? So yeah, let's talk about the reason why we need a lower level language to implement this process exporter. So Mac OS, like I said before, doesn't have a proc file system. So if you're a Linux user, you probably know slash proc on your Linux machine. You could go in there, see the number of processes, and those subfolders. You could see more details about the processes, like the memory, the CPU, the task type, the C groups that it belongs to. But in Mac OS, none of this exists, right? In Mac OS, you have to basically use system calls to get all of that data. First, you could use like libproc or proc PID info to like get process info. Yeah, that is a really good API for that. For system-wide stats, like the total number of processors running on this machine, you could get that with scictl. And therefore, networking stats, that could be gotten with the network statistics API. So we'll get to this later, but it required me, reverse engineering. So because we are using system calls, um, sometimes the kernel doesn't give you permissions to see like some of this data, right? So you basically, a good way to engineer this is that if a call fails, it's best to treat it as missing but not fatal, right? Because you might be able to get the stats for other processes. So yeah. And yeah, let's look at the high level of a process exporter. Um, is basically for each script, get a list of PIDs, right? Ask the operating system of the process IDs running on this machine, right? When you get to this process ID for each of the process IDs, you ask the operating system again, hey, can I get the process info for this PID? And this process info could be, anything basically. It could be the disk IO, the disk metrics of this process, the network metrics of this process, the CPU, the memory, how this process contributes to the battery life, etc, etc. So there are just so many things like you could get from a process info. So yeah, you could group them, and the reason why you group this is that, for example, um let's say Chrome. Let's take Chrome as an example, right? The thing with browsers is that seems like every tab you create, I'm not exactly sure of this, but it seems like every tab you create, that is a process on its own. So we could, group all of this, and these processes are all owned by Chrome, right? So we could just group all of these processes into one and say, hey, like this is the total number of processes. This is the totals of what Google Chrome is using, even though it has so many other sub processes. So now, at a final step, we output this in the Prometheus format. So yeah, let's see what the Prometheus format look like. Okay, we'll get to that in a second. So yeah, getting the data, like how do we get the data, right? Yeah, so for stuff like path tags, CPU, CPU user and system time, we compute it by deltas and also get the previous script. For memory, we get resident memory, virtual memory, via tax info, IO, threads, network, and so forth and so on. So yeah, this is the data model. Basically, everything is put into like I said earlier, like a snapshot. So this is like what basically the struct of a snapshot is. So a one time, let's say a right now snapshot is going to contain a lot of all of these details here: PID, PPID, usernames, etc, etc, etc. And in the next 50 seconds, when we take a snapshot of this process again, um we are going to model it around what you see currently on the struct. So let's see an example of what the output is like on Prometheus. So yeah, so when it's outputted on Prometheus, right? This is what a Prometheus format looks like. First, you see the metric, right? Process CPU usage percentage is the actual metric. Then, what you see within it are basically labels, right? So we say that the group name, and how we make this group name is the process, um, the process name and the process part. And if it has a command line, then we add that into the group name. And then we also add an additional label just for the process name itself. And then we also added another label, which is who is the owner of this process. As you can see, Great owns this process. And the numeric number you see right there is like what is the value at that current point in time. So um, we could see that memory RSS bytes was around 11 MB at that point in time. So um, yeah, and for example, Dix IO was this value at this current point in time. So this is basically was an exporter, right? Um, After getting all of those details, this is how we format it into a Prometheus format that is meant to be consumed by a time series database like Prometheus, for example. So yeah, let's go into the details about like the problems we faced while I was building this. So I started seeing like a lot of allocation trash, basically memory, resident memory, and physical footprint was climbing with each script. So millions of I saw a lot of millions of inactive allocations over time, and we'll get to Tracy, but when we viewed Tracy, when we provide with Tracy, the hotspots we are basically in string duplications, grouping, and like not releasing network callbacks data. So yeah, this is a form of dog fooding because right here we are using the process exporter to monitor the process exporter. So you can see that the memory over time in 23 minutes was rising linearly because the process exporter, let's say if for example it does work every 15 seconds, you should see it the ideal memory scenario is for it to spike every 50 seconds, but it's not doing that because it's just rising linearly, right? So this is a bad sign. You could see how it goes from around 50 MB to is that 700 MB in 23 seconds. So that this looks like we have a leak. um so yeah, this is not good at all. So I started diagnosing. So one of the things I did was to use this tool called VMAP to like understand what is actually happening with this process exporter process. And as you can see, we had like 2 million allocations, uh 63 MB swapped out with only 62 allocated. So like with all of these metrics, you could tell that something is wrong, right? Because like why do you have 2 million allocations and very little of them are active, right? Active allocations. We could like from these metrics we could infer that something's wrong and we are doing a lot of allocations that we shouldn't be doing. And so, yes, I started profiling with Tracy. So, Tracy is a real-time profiler. It's basically it's mostly used in the gaming industry and in C and C++. And so, Zig Excellent C interrupts shines here again because it was very easy to integrate it to my Zig project. And yeah, as a side note, this is like the best profiling experience I've ever had. So you should check Tracy out. I'm basically a Tracy champion at this moment. Yeah, so profiling with Tracy, as you can see right here, we had 4.7 million allocation with just 2,000 active.
that tells you that we're doing a lot of little allocations, and all of this accumulate with time, which is not really the way to go about this. And from there, if you look at the callbacks there, um, you could see that there's a lot of hotspots. So I'll just pick one, and that hotspot you see there is every time that we format the Prometheus metrics. Yeah, every time that we format the Prometheus metrics, there was a callback there. Like we are always not callback, sorry. Every time we format the Prometheus matrix, we kept increasing the buffer size because we had like a small buffer. And yeah, so why we kept rebuilding strings and maps? Like, why was all of this happening? We kept rebuilding strings and maps at every script. um Group keys we are built as new hoops, heap strings. We kept repeating dupes for names, usernames, CMD lines, even when on these things don't change that much, right? For example, on a typical Mac OS, you probably have 23, maybe 25 users, and a lot of them are system users, right? So like, these don't change at every script. You don't create users at every script. So the CMD lines, they do change, but they don't change a lot. All of these things are quite static. Even the process names don't change a lot. And from our network start implementation, we allocate for the UID strings, and keep it forever, even when that socket probably has closed. So this was the reason why we were facing all of these issues. So, looking at all of this from a high level, I decided, okay, that's what I'm going to adopt a memory strategy on how to, resolve all of these issues. So one of the memory strategy right there is to borrow by default and own when necessary. And like, if something is already in a heap, just borrow it without having to recreate ours, right? We allocate once and reuse hot buffers instead of allocating so many times. We also like precise hot maps, right? We can probably tell, oh, okay, do some heuristics that, well, like, the total number of users on this system is probably on a typical Mac OS is 23, right? So we could probably precise, do some heuristics and say, okay, let's allocate 16 KB right here. And if it's not if 60 KB can't contain it, then you should expand the map. But um expand the map, but that, like, precising would like reduce the number of allocations we have to do every time. Like, we have to increase the map size. And then also we also like differentiate like the lifetimes, right? Know what should be based on request, what is script, and what is long lived, right? So, and also intent stable strings, and cache mutable ones. In the case of like the um usernames, the process names, the CMD lines, right? These things don't change a lot, right? So we could probably cache them, and intent ones that are always the same. So yeah, this is literally a code description, or like a code sample of um how we group create tree sorry how we group keys, and how we also free them right here. And yeah, this is also another example of how we do caching, like a generation based cache. So we cache stuff that we think we cache stuff that we think doesn't change, and we also intend strings that are hot, that is always being reused. And yeah, so like for the formatting, for the Prometheus formatting, where we try to format like in the Prometheus style. As you can see, like we use a clear retaining capacity. So every time that we do each script, every time this is a script, we keep the capacity but drop the length or drop the content, so we don't have to, in case, just in case we have to, you know um expand the map, the buffer size, we don't have to do another allocation, right? So we just, clear it and keep, and we just clear the buffer and keep that same capacity instead of like making a smaller one. Yeah. And so, what are the lessons I learned from all of this? So, it's basically, to recreate the structure at each script, but not data that can be cached. So, always cache stuff where possible. So, be explicit about ownership. If something already exists in memory, you could just use a pointer to that and just borrow, right? A cheap previous snapshot is always rich for enough for rich metrics. And when you make changes, right, like when you detect issues, and you um, maybe apply some fixes, profiling is the only way to confirm like that this stuff made improvements. So yeah, that is going to be the lessons I learned from this. And yeah, like we went from 50 to 700 MB in 23 minutes. And the results of like this careful, you know memory management, this careful uh, memory philosophy on how we are going to manage, all of these lifetimes. The result of it is that like the exporter, um, you know, um, got to a peak of 32 MB in 2 weeks, like running for 2 weeks. So yeah, this is another form of dog fooding right here. And as you can see, we have made improvements. And one thing I really I really loved seeing here was like the charts go up and down, because like I said, the exporter is expected to do work every 15 seconds. So if that's the case, right? If there's no memory leak, then it should only have those spikes around every 15 seconds. So yeah, this was the result of it, and it seems like we're looking good on this end. And yeah, and also something I would like to add to this is that a process exporter is basically a daemon, right, that watches other processes. So one reason why I was kind of deliberate about the performance of this, about how much memory is going to use, is that you don't want um you don't want a daemon, right, that is monitoring other processes to be using a lot of memory, because it's basically competing with resources with your it's basically competing with compute resources with your other processes. So that is not the ID case. In most cases, you see people like uninstall stuff like this, because why is something that is supposed to monitor my my computer or my server competing with for resources with my other priority workloads. So yeah, that was one of the intentions behind being deliberate about this process exporter using as low memory as possible. So yeah, let's get into um the bonus, because it looks like we have some time. So yeah, process metrics on macOS. Process metrics on macOS is kind of tricky and difficult. I Because like a lot of these metrics are basically behind a private API. So basically, a private API is undocumented API provided by Apple on macOS operating systems. So the high level approach here is basically to create a manager, right, that discovers these best socket sources. So you attach two callbacks to it. The description block is to like get metadata, of the socket and also like the socket life cycle. Then the counts block is to get cumulative bytes, packet counters, and there are also like several more details in it, right? So from the callback dictionaries, like for example, the description ones, you could get the ID of the process that own that socket, the UUID, the process name, etc, etc. And like if what is the provider, is it TCP, is it TCP socket, or is it UDP socket, right? And what is the TCP state, right? Is it closed, is it open, and so forth and so on. On the count block, you can get stuff like TX, r- read and receive and transmit bytes, receive and transmit packets. So in our own implementation, what we do is like record each socket by the UID, then we compute deltas versus the previous snapshot. So deltas is just basically current minus previous. So we fold all of these socket deltas into PID totals for Prometheus. And then when a socket, for example, closes, um, for example, when a socket closes, the when the socket closes, it becomes a closed or time wait. So we just drop that socket from the map. So yeah, the end-to-end flow is basically create the manager, source added block, set the description counts, the and like basically these are basically the block names. So yeah, these are basically the block names. I would probably link an example on how to do this, but the code is right here. So yeah, let's look at the code. So, basically, you create the manager, right? You have to create the manager with like an allocator, and then you set some flags. You set the flags, then you also set like the um, manager, the add TCP with filter and UDP. So 00 here means enabling it. I don't really know what is the last argument, but the second argument sets it to true. So this is an example of a source added callback, um, which we use for each socket, right? So you copy from the description block, you copy from the counts block, and then you do some append, right? Like I said previously, to get the metadata like PIDs, addresses, states, etc, etc, that can be gotten from the description block. Then for the counts block, you can get stuff like the live, um, receive, the live packets, the live bytes transmitted and received, and also the same for sockets, for packets. Sorry. Then for query description, like it's not so necessary, but you could use it to seed your initial snapshot. So yeah, um, for this is an implementation of the counts callback implementation. So basically, what we are doing here is get the values from those fields, like the UID at first. Then we do the same for our XTX bytes and our XTX packets. We compute the data and then we put them in the map as a total, basically. So yeah, the implementation is quite straightforward to do this, just in case you have to like implement a per process network starts on macOS. A lot of something I've seen people do is use NetStop. But if you want something that is more programmatic, then you could basically write this around the API. So yes, I guess we'll be done. That is all for the process exporter. Um, yeah, I would be taking questions at this point. I remember a question that said that talked about compile time allocation. The answer to that is that basically we can't do that compile time allocation because a process like process environments, right? Like when it comes to processes, right? You are dealing with something that is that has a lot of variables, right? For example, you could have a 500 process system, a 500 process server, and the next server could be 1005. So there is no really um, um, opportunities, or how we can tell beforehand at compile time that, oh, like, this is the allocation we need for this specific this is the number of memory, this is how much memory we need to allocate for this data structure. So it's a variable environment, so we can't really do that. So yeah, I hope that answered the question. And yeah, thank you so much. You can find me online. Zero is great on Twitter. I have my LinkedIn pasted up there. And if you like to talk more about this, yeah, my email is available, great@linux.com. So yeah, reach me out. So thank you. Thank you to the organizers for this one. I guess I'll see everyone later. Bye.